So it's now time to start looking at electrical forces and electrical fields. If we can compare them to gravitational, we can start with the gravitational force one there. That's the force between any two masses. It turns out if you have any two charges near each other, or 2 point charges near each other, and these times we do opposite charges, you'll also get a force. And this time it's an electrical force, and it's going to be equal on each object and in opposite directions, so it's still consistent with Newton's third law that a body A exerts a force on body B. You get an equal and opposite force on body A. So those two forces are equal and opposite, and this time the size of the force will be depending on the charges of the objects. Now it's the quantity of charge in excess there, and the quantity of charge in excess there, charge 2. So they use Q for charge there, and it's measured in coulombs with a big C. So we've got some charges there, and again it's the distance between the centres is important, and you can call that D or R. So you're going to find the same sort of thing as before here. Instead of masses, we're going to be using quantities of charge. Yeah, so Q1, Q2 multiplied together, that's proportional to F, but it's inversely proportional to the square of the distance, and you can use that as a D or an R. So what we need here then is a constant to get this into newtons. So we use gravitational constant here. If there's a constant here, you can just use as a K to start with in stage 1, and basically K is equal to 9 by 10 to the 9. So it's a much bigger constant than the gravitational one, which is 6.67 by 10 to the minus 11. So it's a much bigger force you're going to get, and it's easier to sort of see these forces in the lab and see significant accelerations and movement. You'll also see it written in the year 12 paper as 1 over 4 pi epsilon naught, and that means the same thing as that K. It's 9 by 10 to the 9 as a whole thing, so you can use it like that. So just remember it's the same sort of law here. I guess the differences are there's a stronger force because of the different size charge there, and this, apart from just being attractive, can also be repulsive, so that if these are both positive they would repel each other and the force would be going away. So you've got to bear that in mind, that you get some repulsive forces as well as attractive there. So let's look at some examples of this here. So if we look at Coulomb's law here a bit more neatly, we've got the attractive forces here involved, equal and opposite. They've used R in this particular example here, and repulsive forces. So the force between them will be based on F equals K Q1 Q2 on R squared, or D squared, and your constant can be used like that. So I'm going to just use K for stage 1. So some examples of this then. If two charges were separated by distance R, you could have that sort of diagram going on, and that's the force we're using. Based on that force formula, if R is doubled then, and you actually make these so they're twice as far away, the force is spreading out, the force is getting weaker. There's an analogy there that if you were to go twice as far away from a light source, the actual light intensity on a piece of cardboard will be twice as wide and spread over twice the height, which means it's going to spread over 4 times the area, 2 times 2. If it spreads over 4 times the area, the forces are quartered. Okay, so in this case here, we're going to double the distance between them. We would expect it's only going to be 1/4 of the original force. Okay, because an inverse square law, if you put 2R in there, you're going to get 1 over 2 squared, which is 1/4 of the force, or 4 times smaller if you like. Okay, so as you're increasing R, force will go down by what factor? A square factor. So 2 squared is 4. If you just increase the quantity of one charge by double there in this case, or 2 times, that Q1 is 2 times bigger. This whole formula will become 2 times bigger, so force is 2 times bigger, so you get 2F. Now you could be asked a much harder question there where they double both charges and also halve the radius. So in the case of doubling both, you're going to 2 times there and 2 times there, so 2 2s are 4 times bigger for the force. So you're also halving the radius, so if you halve the radius, you're going to bring it twice as close here. The force is going to get stronger. And halving it's going to be 4 times stronger, because you have to do the 2 times smaller radius means 4 times stronger force. Okay, so 4 times stronger on this count, 4 times stronger on the other count should be 16F. All right. You can do some calculations with this involving different units. So this has been given to you in micro coulombs. Now on the front of your formula sheet, it actually tells you that a micro is 10 to the minus 6, so you can cheat and not actually have to think about that conversion. If you're after the force between them then, you're going to use that same formula, substitute in your 9 by 10 to the 9, 3, now as I said a micro, if you just look that up in the formula sheet, it'll say 10 to the minus 6 on a table, so all you need to do is hit your exponent button there, or your times 10 to the x button on your calculator, and then just put that minus 6 in. It'll do it for you in one go. 3, exp button, minus 6, 3, exp button, minus 6, and if you can't convert centimetres here, you could do this as 50, and look up centi on a formula sheet, and it's 10 to the minus 2, and replace that as 0.5, or just leave it as 50 by 10 to minus 2. Don't forget to square it. The answer there then will be about 0.324 newtons, so we should probably round it off to sort of one significant figure really, because I'm only using one in this case here. Alright, you could also do another example here. Two conductors of the same size charge experience a force of 300 when they're 20 centimetres apart. Calculate the charge. So this time we're being asked to go backwards. They've told you the force between these two objects, or these two charges. They've told you they're the same, but you have to work out the charge. So substituting in for force there of 300 and the distance of 0.2, 20 centimetres, that would be your first step. And you can put this in as Q times Q because they're both the same charge, so you don't have to leave them as two separate different ones. Q times Q, of course, is Q squared. The next step is to rearrange. So we're going to do is this divide by 0.2 squared and bring it up here and times by 0.2 squared, or 0.04, which is here. Instead of times by 9 by 10 to the 9, we're going to divide by 9 by 10 to the 9. So all I've done there is leave the Q's on their own and move the other stuff away from it and do the opposite operations. If you're dividing your times, if you're timing, you divide. Now Q times Q is Q squared, not 2Q. So your next line will be to square root that value to get Q on its own, and there's your charge in coulombs, which is a pretty small charge.